The main thing to get a sense for today, the first thing really is the goals of the course. And there's really three of them, and they align nicely with the questions people answered in the online quiz as to what they hope to get out of it, what they saw challenging. The first is what I would call put those finishing touches on your math. You've had, roughly 6 quarters of math through the math department, depending what you placed out of, what you placed into, how many you've taken previously, whether you're doing stuff concurrently. It's been siloed into fixed courses. You haven't had to deal with it sort of all at once in an integrated fashion. There may be things that you found easy, things you found hard. Not all math topics you had are relevant to your physics. So this is kind of to go through that and what I would call clean that up. And right in that is really to provide a framework for why the math you learned we're going to use in physics. I try very hard. So in this regard, there will be a big difference, most of the time, a pretty big difference between what I am doing in lecture and what is in the BOAS reading. The BOAS is about doing the math. So the reading will be very specific, give you the, how you do it, the details of that. I will be doing how you do the math too, to a large extent, but everything I will do will be focused and aimed at why would we use this in physics, where would we use this in physics, why do physicists care about that? That tends to be my focus and priority. There we go. Hopefully it won't show that again. And then the third one really is this Mathematica issue, to give you the basic skills in Mathematica. And it's very useful in a lot of our upper division courses. It depends who you have. You will use more or less Mathematica in your classical mechanics, E&M, quantum mechanics courses. Some use a lot, some use less. You should always check, but in fact, most faculty, if you get really good at typing solutions in Mathematica, even if they're handed in paper ones, if you format it nicely and print it, that is much more fun to read than handwritten solutions. And once you get good at Mathematica, you'll find you can do those solutions quite quickly. And a happy grader is one who's likely to give you more points. But one of the things about Mathematica, and I want to go back to the Dropbox here briefly, whoops, is there are lots of ways to often do things. And I really want to encourage you to use this shared student files. I'll be showing you one way or how to do things. I find the students, particularly ones who are very computer inclined, quickly find cooler formatting, better ways to prepare the text, shortcuts to things, keyboard shortcuts. You find anything interesting or cool, post it for your fellow students. Keep in mind there's no curve in this class. You can all get A's. So it really is a class where you can share this information and knowledge with each other. And with Mathematica, that's particularly helpful. So I do encourage people to use this shared student file to share with each other good ways or tricks if you find for doing stuff. That in this class is not considered cheating. So feel free to share any Mathematica ideas with each other. Now, the other issue that I like to go over is, given that these are the goals, the real question is how to achieve these. And when students first look at my courses, typically at the websites, and as some of you said this, they're like, oh my God, there's so much stuff to keep track of. That's the hard challenge. How am I going to do all of this? I've done this hopefully long enough and well enough. It actually is all designed with a purpose. So the lecture, and the readings, that's really about giving you the key information that you need for the course. The stuff, the details of how to do things, why we're doing it, all of that. the pre-assignments. That's critical for both of us. To figure out where we are in the class. Okay? I need to know what it is you know and don't know. So I already know, for instance, by asking you to find the magnitude of 3 plus 4i, that pretty much all of you can do that. We don't have to spend a lot of time on that particular problem. That hasn't been true every year I taught the course. A lot depends on where the math classes put in their complex analysis. And if I decide, oh, most of the class got something right, and we're not going to do much on it, and you got it wrong, you need to know, okay, did I just make a careless error there, but I really know how to do that? Or is that something I actually don't know how to do? Professor Dennin's assuming I know how to do it, so I better meet with him his office hours, I better find the TA, I better figure out how to know that stuff, talk to somebody else in the class. So in these pre-assignments, keep in mind that most of them, my assumption is, you all know how to do everything in the pre-assignments, whether it's the homework problems or a quiz I happen to post. Except, of course, the Mathematica stuff. The reason it's a pre-assignment is I think it's easy enough to learn on your own by going through the tutorial. So that's both a check for you and a check for me. The problem-solving sessions are key. Because this is the one place you get and I get real-time feedback. That's where we're doing the challenging problems in the course, trying to push a little bit farther than we might otherwise, but doing it in an environment where I can see immediately what mistakes you're making, you can see immediately what mistakes you're making, and there can be that real-time feedback, and that's critical, and that really prepares you for the harder problems in the homework and for the exam problems. Obviously, the exams are key. I find the only things I really remember are the things I got wrong on exams, and there's a reason I give you 4 exams before the final. The 4 exams in class are really a chance to make sure and double check, do I really know all this stuff? Because until you do it under time conditions on your own, you're just not going to know if you really know it yet or not.
The final exam?
Well, and the final exam is also a great place to learn stuff, but hopefully by then you've learned it all in the 4 exams. So there's 4 in-class exams plus a final. So it's 4 plus 1. What it means is you'll have had an exam on every topic that's going to show up on the final. So that's a useful thing going into the final. And then a lot of students often complain about stuff that they declare to be busy work. But it's math. You just have to practice a lot of stuff. You just have to drill and practice. And so there are a lot of things that, if you're doing it and you've got it mastered, doing more of it may not help you. And so those are things you can probably spend less time on and ignore. But until you actually have it mastered, you really need to do it. So that's the design of the course. Any questions on that? I just like to be upfront with why I put each piece in the course, where I put it, and how we're doing it. The other thing, just to give you an overview, the topics we'll be doing. We're going to start with series and complex numbers. We're then going to go into matrices. And the first thing we'll do is just review the mechanics, how to use matrices, determinants, multiply, add, subtract, all those good things. With complex numbers, we're going to focus, and series, why we use them in physics, because there's a lot of math machinery that you learned that doesn't necessarily get used a lot in the physics class. Right after doing matrices, we're going to go into linear vector spaces. This will be an interesting place because I know the math curriculum has reorganized. In the past, half the students typically had not really done a lot with linear vector spaces. So this is where the pre-quiz will become key, because I'm going to have to get a sense where this class is. They've reorganized this some, and you may know more than past classes have, and we'll adjust for that. But this is essential for so much of physics, and it really uses the matrices a lot. Then we're going to go into Fourier techniques. Just out of curiosity, how many have already done Fourier series? If you've done Fourier series, raise your hand. Okay? This is a great example of linear vector spaces, so we're going to do it from the physics point of view of this being a linear vector space, not necessarily the math class point of view, which I think really will help and are something that you'll use a lot. We spend a little bit of time reviewing differential equations and partial differential equations. The reason there is you've all had or are taking concurrently the math differential equation course, right? Yes? Say yes. No, but you did the differential equation. Yeah. And so we just highlight a few things from that class that you use a lot in physics. And there's just one or two things that you will use a lot going forward. Some of these topics, like the partial differential equation, a lot of topics you don't really learn until the second or third time you saw them. So some things in this class, like differential equations, are a review. I expect you to have seen it. We're going to review it, and so on, or you might be taking it concurrently. Partial differential equations, this will be the first time you see it. I don't necessarily expect you to master it in this class, but when you see it again next year in your E&M class, you'll be prepared to then understand it the second time you see it. So there are things that I actually don't expect you to understand the first time. And then we close by reviewing vector calculus and integration, just because of how much they're used. And really, the unifying theme for the whole thing is how do physicists use all these topics. So these are the topics we're going through.